This video, I'm just going to do a quick review of stress analysis from your statics and strength and materials class. And some of you may have also covered this in machine design. Since we have most of the design done, what we want to do is take a step back and perform a stress analysis on some of the critical areas of the vehicles. So once we do that, we can be sure that the design is good in terms of materials choice and size of components and so forth. If not, then we'd go in and do some revisions to the design. I'll just go through, take a few seconds, go through each of the different types of stresses. There's direct normal stress, and that's tension and compression. That's the simplest, most basic kind of stress. The formula is stress is equal to force over area. So you can think about a bar in either tension or compression and how the fibers of the material are feeling pulled apart or they're feeling crushed. Next type of stress is torsional shear stress. So think about a rotating shaft. As you twist that shaft as it tries to generate power from one end to the other, then you're going to create a torsional type of stress. Now, torsion is a tau type of stress. The material that makes up that component, it feels like it's being sheared or cleaved apart. So the action is different, the type of stress is different. So pay attention to that. It's different than a normal stress. The formula we use for torsional shear stress is tau is equal to Tc times K sub T divided by J, where T is the torque value, C would be the radius of the shaft, K sub T is our stress concentration factor. For example, if we have a keyway or if we have a hole in the shaft or maybe a step down in the shaft. J is your polar section modulus, and that's just a value you calculate based on the diameter of the shaft. Next, we'll talk about direct shear stress. So again, this is a classic example of a shear where the fibers of the material feel like they're being sheared or cleaved apart. They're not crushed or pulled apart. Think about like two plates, as this example on the right shows you. You got those two plates that are bolted together. As you try to pull them apart, the bolt or the rivet there is going to be sheared when you reach a maximum kind of limit. The calculation is relatively straightforward. It's tau is equal to force over the area of the shear, which in this example would just be the cross-section area of the fastener. Next, we'll talk about bending stress. So bending is a little more complicated. Think about a beam. Now, a beam could be anything. It could be a shaft, for example, that has a gear in the middle of it, and that force is going to tend to cause that shaft to bend or that beam to bend. It's a normal type stress because the way the fibers of the material feel that bending. If you look at the example on the right, the load pushing down is going to cause the fibers on the top of the shaft to be forced to be in compression. They're going to try to crush each other. And the fibers on the bottom of the beam, as the beam bends, they're going to be pulled apart. So it actually generates a tensile stress along the outside surface. So that's why it's a normal type stress. The formula is my over I or mc over I. You would need to determine the bending moment from a shear and bending moment diagram. The y value is typically it's just the radius of the shaft, and then you'd have to calculate the moment of inertia of the cross-section area of that shaft. When you're doing calculations like this, there's a lot of different things that are being built into the formulas that we use. You have to really pay close attention to the units and always write out your units when you're doing your calculations. It's going to be a check on the value that you get, because if the unit is correct, it's a pretty good chance your value is correct. If the unit's wrong, I would go back and check everything because you may have missed a conversion or something. We typically do all our calculations in English units in this class. In terms of PSI, it's going to be pounds per square inch. So any force that you're dealing with should be in pounds, and any area that you're dealing with should be in inches squared. Design stress is a critical item to talk about because it's one thing to calculate the value of stress, but you have to have sort of a benchmark, something to look at and say, is this an acceptable amount of stress? And that's exactly what the design stress is. In order to do that, what we do is calculate a value. Now, if it's a normal stress, it would be a sigma design. So there'd be a design stress for a normal stress type situation, tension or compression or bending. And we have a tau design, which is for shearing type of stress. So if you look at those formulas, they're different. Materials are actually about 60% as strong in shear as they are under tension or compression. So the tau design formula is different than the sigma design, so pay attention to that. There's going to be based on the yield strength of the material. So you'd look up the particular material you're using, you'd look up that yield strength, and then the design factor. Here's a table that's a generally accepted type of table, and what you would look at is the type of material do you have. What do you have here? It's a ductile or brittle. Now, typically you try to use a ductile type material because it's much more forgiving. And then what kind of load do you have, a static or a dynamic load? Dynamic load would mean that it's changing or the thing is moving, and typically you would use a dynamic load in most designs. As you've done before in your other engineering classes, I'm sure you've seen this table in your strength of materials class as well as your engineering materials class. For a known material, there's published values that give you the limits of the capability of that material, and those limits are reported as ultimate strength and yield strength. So the ultimate strength would be the maximum amount of stress you could put on that material before it fails, and the yield strength would be the maximum amount of stress you could put on the material before it permanently yields or permanently deforms. So for example, in that previous slide, we were talking about design factor. Design stress, it's based on the yield strength. So you would look up your particular material and go down the table and grab a value. Now pay attention because these numbers are reported in KSI, which is 1,000 PSI. So for example, if it says 60 KSI, that's 60,000 PSI. Another thing you might want to know is the density of steel. For example, we need to determine the weight of a component. With tubing, we typically just use low carbon steel, and that's an easy value to look up. Now, the odd part about it is it's typically reported in grams per cubic centimeter. So if you have, for example, a volume in cubic inches, you're going to have to make a conversion in order to find the actual mass or the weight of that part, or you can find another table that has it in pounds per cubic inch. As I mentioned earlier, one of the things we have to deal with is stress concentrations. So when you're dealing with shafts, that would typically mean that you have a keyway. If you're driving a component, a sprocket, or a gear, for example, you're going to cut a keyway in the shaft as well as the hub of the gear or sprocket, and that's how you would transmit torque through that component. You can use a standard table like this to determine what the stress concentration value is that's created with the key seat. Now, the reason it's a stress concentration is because it creates a weak spot in the component, and you need to incorporate that into your selection of material and the size of that component. So you can use a table like this to find the value of K sub T. Another value you may need to know in your calculations, specifically when you start talking about bending stress or horizontal shear stress, is the moment of inertia. Now, the moment of inertia is the strength of the shape of a part. Now, there's a strength based on the material, and that's what we just looked at, the yield strength and ultimate strength. And there's a strength of a shape. For example, different shapes are stronger than others. So it's a simple matter of looking up in the table here. Like for example, if it's a rectangular part, you can look at the moment of inertia about the x-axis. It's BH cubed over 12. So you just plug in those dimensions. If it's a solid round part, like a solid bar, then it's pi d to the fourth over 64th and so forth. Now, one thing you may want to do in your design, maybe ask to do that, is to determine if you're using the right size chain. Chains come in lots of different sizes here. This is just a piece of a table for a roller chain, a size 25. Now that's a pretty small size chain. That might be something you use on like a kid's bike or something. You can see it. They report the maximum tensile strength you can put on that chain. In this case, it's a small chain, but it could still hold 780 pounds. Now, one thing I will tell you is roller chain is not really designed to be used to lift loads, but it will definitely have a tensile strength because that's how it works. For example, one sprocket to another, the chain, the force in the chain is what's going to rotate those sprockets. So you can just look up a table online and find values for chain strengths. For this assignment, several things I'll have you do for the stress analysis portion. One is calculate the frame weight. So just the frame. Hopefully you have created your parts, your tubing parts as being hollow, and you'd use appropriate size. Any flat plates are not too thick and those kinds of things. Break it down to where it's the frame and the brackets and those kinds of things on there, and then determine the weight. And you can do that easily using your CAD software. I also want you to find out the sprocket sizes. So we're going to do that by looking at the maximum speed we're looking for and determine the gear ratio, and then choosing the sprockets to get to that appropriate speed. And what we said was somewhere around 25 miles an hour is what we're going for. The third one is calculate the torsional shear stress in the jack shaft. The fourth is to calculate the torsional shear stress in the rear axle. Now, both of those can be done. It's a similar process using that tau equals TC times K sub T over J formula. And the fifth item is calculate the actual force on the rear shock absorbers.